This is a straight line. Add some more to it and we get a rectangle, or more precisely, something in 2 dimensions. Add some more lines and you get something in 3 dimensions. Now, flex your muscles and add some more lines and you get what? Yes, a 4-dimensional something that may look something like this. Doesn't it seem to go back to 2D? Well, it may seem that way, but this is actually something in 4 dimensions. And in this video, I'll explain this to you. But before that, let me tell you something, that space has always remained an intriguing area of science for humanity. Whatever secrets are held by it have remained, it's us who have gradually deciphered them as our technology has evolved with time. And let me tell you, we have actually dug quite deeper into astrophysics and have uncovered some great deal of secrets. However, that in no way means that we have explored space inside out. Nope, absolutely not. Space is way more diverse, which is why discoveries in space have always been enigmatic, and one of these discoveries was the concept of spacetime. This is just another one of our exciting expeditions where we will try our best to expand the horizons of your understanding and take you on a journey that for many humans is a journey beyond their understanding. So make no mistakes in being all ears until the end of this video to get to know everything about something. Since the early times of astrophysics, the idea of gravity has remained very interesting. I mean, something falling towards another thing without the two things even coming into contact? Sounds like magic, and it surely is. No wonder why Isaac Newton's curiosity was tapped when an apple fell from a tree and hit his head. He went straight to work and discovered something extremely interesting. He explained that between any 2 objects in the universe, there exists a force of attraction under the influence of which the 2 objects would attract towards one another. He further explained that this force was related to the masses of those objects and the distance between them. Such was the relationship that as the masses increased, attraction between them would also increase. But as the distance between them increased, the force of attraction between the objects would significantly decrease. In mathematical terms, attraction between 2 objects was proportional to their masses, but inversely proportional to the distance between them. This force of attraction is what was called gravity. And Newton's discovery of this force helped us understand the behavior of many objects in the universe. As a matter of fact, Newton's explanation was even valid for normal objects, for example, between 2 people. Although this concept remained popular, but curious minds like you and me kept thinking, fine, the 2 objects attract each other, but what actually is happening that is causing the attraction? And one of these curious minds happened to be none other than the famous Albert Einstein, who lent some thought to this idea and ended up discovering that same something we were talking about at the start of this video. That's right, over the years, Einstein formulated 2 theories, general relativity and special relativity. In these 2 theories, Einstein did a job well done in explaining gravity more accurately, or I would say, more like the how it's done kind of way. Einstein explained that the 3 dimensions of space, that are length, width, and height, when combined with the 4th dimension of time, formed a 4-dimensional something that looked like a fabric, and was termed spacetime. He further explained that gravity was the effect of objects falling towards other more massive objects, because of the curvature caused in the fabric of spacetime by massive bodies. This idea perfectly explained the attraction between 2 objects, however, was in stark contrast to Newton's explanation of gravity in 2 ways. Number 1, according to Einstein's theory, gravity was not a force, as explained by Newton, but instead the effect of the curvature. And number 2, that gravity was an effect visible on smaller, less massive objects rather than both the objects. This is how the concept of spacetime brilliantly explained the concept of gravity and went on to lay the foundations for more modern physics, and most thanks to one genius man, Albert Einstein, and the little remaining thanks to Isaac Newton for actually giving thought to gravity. Because the concept of spacetime revolutionized the way of how we thought the universe was. In fact, the concept of spacetime greatly helped us in understanding the structure of the universe as well as the behavior of certain celestial bodies and phenomena. Let's take a look at a few. Black holes. Black holes are created from the remnants of massive stars that have exhausted their nuclear fuel and have undergone a violent supernova explosion. The core of the star collapses under the relentless pull of gravity, and as it shrinks, it causes an intense warp in the fabric of spacetime around it. At the heart of a black hole is an invisible boundary called the event horizon. Once an object, including light, crosses this boundary, it's trapped by the black hole's gravity and can never escape. This happens because the warping of spacetime near the black hole becomes so extreme that the escape velocity exceeds the speed of light. Einstein rings. When a massive object, like a galaxy, is positioned between a distant light source, such as a more distant galaxy or quasar, and an observer on Earth, it acts like a gravitational lens. The mass of the foreground object causes spacetime to curve around it. This curvature affects the path that light follows as it travels from the distant source to the observer. As the light from the distant source passes through the curved spacetime near the foreground object, its path is bent. This bending can be so pronounced that the light rays converge and create a circular or near-circular pattern of light in the observer's sky. What an observer sees from Earth is an almost perfect ring of light known as an Einstein ring. The light source, the lensing object, and the observer are perfectly aligned, creating this stunning and symmetrical ring of light. Objects in freefall. When you drop an object on Earth, it appears to fall downward. In reality, it's following a geodesic, which is the shortest path through the curved spacetime. The object is not pulled by a force, it's just moving naturally along this path. Geodesics are like the straightest possible lines in curved spacetime. They represent the paths that objects would follow without any forces acting on them. It's as if objects are just obeying the natural shape of spacetime in their vicinity. The motion of planets and other celestial objects in orbit around a star is also described by geodesics. Planets are essentially falling towards the star, but their tangential velocity keeps them in a stable orbit, following the geodesics around the star's curvature. Astronauts aboard the International Space Station, for example, experience a sensation of weightlessness. This is because the space station is in freefall around Earth, and the astronauts are also in freefall inside the station, following geodesics. This creates the feeling of weightlessness, even though gravity is still at work. Time dilation. When you are in a region of strong gravity, like near a massive planet or star, space-time is significantly curved. This curvature affects how time passes for you compared to someone in a weaker gravitational field. Essentially, time runs slower in stronger gravity. Imagine two clocks, one placed near the massive object and the other farther away in weaker gravity. The clock in the stronger gravity will tick more slowly. This isn't just a matter of perception, it's a physical effect. Time dilation is one of the key components of Einstein's theory of relativity. It means that time is relative. It's not an absolute concept, but depends on your motion and the strength of gravity where you are. Time dilation has practical implications. For example, it's taken into account in the operation of the Global Positioning System (GPS) because the satellites in orbit experience slightly weaker gravity, which makes their onboard clocks run a bit faster compared to Earth's surface clocks. And this is how the concept of spacetime, introduced by Albert Einstein, went on to revolutionize the way gravity works and how many other celestial bodies behave and phenomena take place. I hope you enjoyed this video, and if you did, take a moment to hit the like and subscribe buttons, and ring the bell icon before leaving to stay tuned about our next videos. Until we are working hard to produce our next interesting expedition, take some time out to watch some of our other interesting videos and tap your curiosity just like Einstein did. And let me tell you something interesting, this is the end for this video. See you in another video.